Okay. So okay, very good. So last lecture, we were talking about, we were going over some programs in standard ML, and let's pick up right from where we left off. So what we are going to talk about today is data types in standard ML, and the data types in ML are very much modeled after the types of data that we studied in this course, such as sets and Cartesian products of sets and sequences and so on. Okay, so so let's try to quickly understand what these types mean, and what how we use them. Okay, so sets are the most fundamental types. Typically, you have certain built-in types such as integers and reals and so on, and these are finite subsets of you know the set of natural numbers or integers that we talk about. I guess, and then real numbers, once again, are basically a finite subset of the set of real numbers, and so on. You can also define, programmer can define their own set of data using, what are called enumerated types. So the way you define an enumerated type in standard ML is, this way. So for instance, you can define suits in, cards using, this type of definition. So you have this set, right? So this type corresponds to the set, right? So this set is being written out using this notation in standard ML. Same way you can define ranks as another enumerated type, which consists of these 13 possibilities. Okay, so then you have, these are by and large what are called, primitive or basic types, and then there are constructed types that are basically constructed from existing types. So tuples correspond to the way we do products on sets. So for instance, you can define card to be the consisting of the pair that whose first component is the suit and the second component is the rank. And so we could then go ahead and define a poker hand as combination of these 5 cards, right? So we have so that is another way of defining a tuple. Okay, so one thing to remember about tuples is that it is not a set, because in a tuple the order matters, right? So we talk about the first component of the tuple, the second component of the tuple, and so on, right? So the order matters, so therefore it's not a set. Okay, and then the third type is what is called a sequence. Sometimes we refer to it as a list. Okay, in standard ML, the term that they use is a list. Okay, so if we try to define a sequence using the notation that we have used for sets in this course, then this will be the set. It is the union of powers of the set S, right? So S, so this is S0 union s to the power 1 union s to the power 2 and so on, right? So s0 corresponds to just or s to the power 0 corresponds to a sequence of length 0, which means it's just an empty string. S1 corresponds to a sequence of length 1, or sometimes we call them a string of length 1, right? So that means it has just one element. String s to the power 2 denotes strings of length 2 or sequences of length 2 and so on. So it is these, so this is denoted using what is called a list type in standard ML. So here are some examples. So here is how you, a list in standard ML is represented using square brackets. So you use a square bracket, and then you list the elements of the list inside. Okay, so that's how you make lists. So this is a list that contains exactly one element, which is the number 1. And here is a list of real numbers, right? So it has 3 elements, 4.1, 2.7, and 3.1. The lists in ML have to have the same type, right? So it's a homogeneous sequence, right? So every element of the list has the same type. So when you create what appears to be a list that consists of both integers and real numbers, ML doesn't like it, and it gives you, this angry message. So hopefully you'll know better next time and not, say this to ML again. So you can also have lists of lists, right? So here is a list which consists of 2 elements, each of which itself is a list. Okay, and once again, this outer list, the elements of the outer list have to have the same type. So for instance, if you tried something like then ML will again complain with an even longer message than this one, telling you that somehow this one, if it's an integer in this list, then this should be a list of integers as well, right? So everything has to have the exact same type. Okay. So the empty list is denoted using these empty square brackets. The alternate way to refer to an empty list is as nil. Okay, NIL is another way to express it. Okay, so let's. So one other thing that I want to mention here is that although we tend to write in all these examples, we have tended to write lists using a sequence where everything is like we put a comma in between. A better way or the more correct way to think about a list is that it has a first element, and then there is the rest of the list. Okay, so this first element is called the head of the list, and the rest of the element list is called the tail of the list. Okay, so you think of a list as containing 2 components. The first component is the first element of the list, and the second component is the rest of the list. Okay, and the tail, of course, contains, has the same structure. The tail has its own first element, and then it has, that is the tail of the tail. And the tail of the tail is, in this case, happens to be the nil list or empty list. Okay, so thinking of lists in this way is important because many times you want to refer to a list where you don't know necessarily the length of the list in advance. Okay, you may know the first element, but you somehow want to manipulate the list without necessarily knowing how many elements are there. And therefore, the best way to do that is by using uh, this double colon symbol, which is uh, pronounced as cons. Okay, as a cons symbol, but basically it's a double colon. Okay, so let's look at some tuple examples. So unlike lists, tuples are heterogeneous. So each component of a tuple can be of a different type. And this is something that you come to expect, because when we say, you know, uh, when we take the Cartesian product of two sets, there is no limitation on, A and B having to be, say subsets of the same set or anything like that. They are arbitrary sets. So the correspondingly, the components of a tuple can have very different types. So here is a tuple which has two components. The first component is an integer, second component is a string, right? So tuples are, ML refers to the type of a tuple by putting a star in the middle. Okay, so it says, so here is a tuple with two components. So it says here is the first component, the type is integer. Here is the second component, the type is a string. And here is a tuple with three components, and then it indicates that using a three-way star, and that identifies that the first component is a Boolean value, the second component is the real value, and the third component is a string. And of course, just as in the case of lists, you can have tuples of tuples. So here you have at the outer level, you have two tuples, and the first tuple is contains two integers, so it's called int cross int. The second component also contains a tuple, so it's called int cross int. Okay, and finally, you can have a list of tuples, so you can combine these two types in whichever way you want. Okay, so but then because lists have to be homogeneous, all of these elements have to have the same type. And then it says, hey, this is a list where each element of the list has this type, right? Each element of the list is a pair, and the first component of that pair is an integer, and the second component is an integer. Okay, so any questions so far? I hope you have been um, keeping up with ML so far, because things are going to get a bit more, you know, faster today. Okay, so but before we do that, let me talk briefly about the midterm, right? So the midterm is Thursday, and the instructions for the midterm were already posted, right? So if you have any questions, now is the time to ask. There are a couple of things I want to emphasize again. First of all, you should have your audio on at all times. Okay, it shouldn't go off at any time. Okay, so we should be able to hear you at all times. And the second thing is that you need to sit a little bit further behind from your screen so that we can see, your hands, right? So your hands should always be within view, and of course your face, right? So between, so essentially the upper half of your body are, if it's not the upper half, then if you keep your, so for instance, the way I'm sitting, obviously you can't see my hands most of the time, so I really have to move back and change my screen. And if I'm going to so for instance, this is not enough, right? So if I sit here and write like this, then that's more or less going to be enough. But then you should basically try this out ahead of time, right? So you can call yourself on Zoom and just try it out, so you know how far you need to sit behind, so that that way you can just get started with the exam and complete it without ever any disturbance. Otherwise, we'll have to, yell at you and scream at you and get your attention and tell you to do, go move farther or whatever, right? So just think about it and plan it a little bit ahead of time. That way, we will the exam will run smoothly, right? So your exam will be something that comes up on Blackboard, and it'll be given to you after you enter your respective rooms, right? And then you'll just bring up the exam on your screen, and um, right. So once you bring up the exam on the screen, then you can start answering it. You write it on using you know on a piece of paper. So make sure that you have a few sheets of paper next to you so that you don't have to get up and move around, right? And once you're done, then you need to tell the TA that you're done, and then scan in your you know paper, and then you can be on your way. Okay. And until that is done, until you're finished scanning it in, you should be continuously on Zoom. And anytime you drop or your audio goes off, that's going to make it hard for us, because that is every such opportunity is every such gap is an opportunity for something to go wrong, and we don't want anything to go wrong, right? So we want to make sure that you are in view all the times, just like the way it would be when you are in a proctored setting for the exam. Any questions?
So I guess that means, what should one, like my Wi-Fi will sometimes just drop for maybe 5 minutes. What should one do in that situation? Because it's not like
So
lockdown.
what did you do? It shouldn't happen, right? So let's hope it doesn't happen.
Right.
Okay, because this is what we are talking about this time is actually less of an issue than uh, when you took the first midterm, right?
I mean, on the first midterm though, it was always recording regardless if we were connected or not, right?
Yeah. And I think I'm pretty sure that any such drops are quite short. So we'll figure out, right? So again, don't plan on being
Yeah,
away
of course.
for any period of time, right? So anything unforeseen that happens, well, obviously we'll have to deal with it, right? So don't stress over things that are outside your control.
All right, thank you.
So we only want to worry about things that are under our control, and let's make sure that those are we plan for uh, you know things to be under our control, and if not, well, there are always ways to deal with it. Okay. Any other questions about the exam?
And I'm to understand you want to see our hands, but does that include our keyboard too when we're typing in our answers?
So you are not going to be doing any typing.
Oh, I see. Okay, it's completely.
So once you bring up your exam, it's basically one page exam, and so there should not be any need to really interact with your computer.
All right, thank you.
Right. So it's just um, okay. Any other questions? So once again, you should really, your best preparation is to work out your homework 4 problems and homework 5 problems once again. And well, if you run out of time, of course, look through the solutions, but the best preparation is to try to redo them yourself, right? And then look through the lecture notes, to the lecture slides, to make sure that you aren't missing anything that may not have been covered um, in the homeworks, right? But obviously that is the order. First do the homework and then look through the slides. Okay. So anything else? Good. Very good. So if you think of anything else, you can, we still have quite some time to go today, right? So we are just going to I'm going to take the recitation today, which means that You have still quite a bit of time. So let's continue with our discussion of functions. Now we have learned about these new data types. Then those data types allow us to write, more functions that can actually do more. Okay, so so very lists are a very important data type in standard ML. So we will use them extensively going forward, right? So till now, we were looking at programs that were just working on integers. From here on, most of the programs we'll work on will be on working on lists. Okay. So I do think there are more people in the class than what I can see. So can a few more of you uh, turn on your cameras? Okay. I'm waiting. So I'll wait for some more time. So we will continue to define, functions inductively, or basically using a base case and recursive case. For integers, typically the base case corresponds to n equal to 0. For lists, typically the base case will correspond to the empty list, right? And we use what is called pattern matching to distinguish between the base case and the recursive case. But on the surface, it doesn't look that different from how we have written recursive functions in the case of integers, where we will have one rule that applies for n equal to 0 and another rule that applies for all values of n other than 0. Right? The same way, we will have one rule that applies to the empty list and another rule that applies to a list that's non-empty. Okay, so and just so that you don't get confused, these two symbols mean exactly the same thing, right? And to reiterate the point about lists, uh, so a non-empty list has a head, which is its first element, and tail, which is the rest of the list. Okay, which includes elements 2 through n, or 2 through the last element of the list. That's going to be in the tail. Okay, and lists have to have a homogeneous type, and uh, often ML will tell you that it is a list, and then the list has a certain type. Okay, if it says a single quote followed by a letter, what that means is that the type can be anything. Okay, and so for instance, if you type just the empty list to ML, it'll just say, okay, it's a list of anything, because, well, obviously it's an empty list, so it could be a list of anything, right? It's you can't tell what its exact type is. But if you write, if once you put an element such as 1, then it knows that, okay, it's a list of integers. Okay, but you can write functions which don't really care about what is the element type. So in which case you can have functions which for which ML will say this function takes lists of any type. Okay, so So again, normally we would, any finite list with a fixed number of elements, we would typically write it down this way, but you can write down, this way, which means that here is the first element, and then that is its tail. And then for the tail, this is the first element, and then it has its own tail. And for that tail, this is the first element, and this is the inner tail, and then that inner tail has this as the head and this as the tail, right? So you have this, recursive structure like peeling an onion, right? So you peel, and then what you see inside is exactly the same thing. Okay, you can, mix the double colon and the square bracket, notations. So for instance, this is exactly the same list as this. And all we have done is, the first two elements are being expressed using the colon notation rather than, comma within a bracket notation. Okay. So why would you do that? Well, that's not my, you may or may not use the two notations. You can, the square bracket notation is not essential, but the const notation, the double colon notation is something that, you will always have in your program, right? So you cannot avoid that, but you can avoid this if you want. So let's look at some example functions on lists. Okay, so here is a function that computes a length of a list. Okay, and we define it, in a recursive way, just as we have done in the past. This one says that an empty list has a length of 0, and this one says that if you have a list which has a first element and then the rest of the list, then it says compute the length of the rest of the list, and then you add 1 to that. That will be the length of this whole list, right? So this is kind of how the recursion works. So it's so for instance, if you give so I'm going to it's so to understand how these programs work, it is helpful to draw the lists, in like a tree. Okay, so what I'm going to do is, here is the const symbol, and so let's say we take this list 1, 2, 3. Okay, using the const notation, this is how it's going to look like. Okay, so here is the first element, and here is the tail, right? And then for the tail, this is the first element, and that is the tail, and so on. Okay, so when you call length on this list, then it's going to take this tree structure and it's going to try to match it against these rules. Well, obviously, this is not an empty list, so it's not going to match the first rule. It's going to match the second rule. And so X is going to get bound to the to 1, and XS is going to get bound to this. Okay, so this is why it's called pattern matching, because you look at the data and you look at the rule, and then you match their structure and then say, hey, this way X should correspond to this thing, and XS should correspond to whatever is on the right hand side of that const symbol. And then you're going to say, hey, then what I need to do is to compute length of XS, which is the length of this right subtree. And this is going to proceed again in the same fashion. Once again, you're going to try to evaluate the length of this. You're going to apply the two rules, and then you will find that, well, it is this rule that's applicable. So once again, you're going to end up calling length on this subtree, which in turn is going to call length on that subtree. Now, length of that subtree is going to come back. And so it's going to be 0, right? And so what's going to happen here is that because this became 0, 1 plus 0 is going to become 1 here. And then again, you're going to add 1 plus whatever is the length that's coming back from here. So this length is going to be 2. And then at the top level, you're going to get length 3. Okay. So there are, of course, two ways to understand any program. One is just to look at the equations and then say, yes, I understand that the length of a list is nothing but 1 plus the length of the everything except the first element, right? Because that's almost the definition of length, right? So length of the whole list is going to be 1 plus whatever is the length of the rest of the list. So we can just understand it at that level mathematically and not really look inside how these function calls work out. And that's most of the time that's how we work, right? Because it's just too painful to sort of draw pictures like this and look at every step of how this is how this is the evaluation works. But there are going to be times when maybe you won't quite understand the equations, and then you have to say, hey, let me imagine how this thing works, and maybe that way I'll understand how this function by sort of stepping through and following every step of how this function works. Okay. So so there are languages in which this is called a linked list, but that's the terminology varies across languages. So if you are programming in Java, then it'll definitely be called a linked list. In functional languages, the terminology is just list, okay, because there is the presence of a link is somehow implicit, and it's not something that that's as visible as in Java. I don't quite know how to explain it to you because we are I'm trying to teach you programming without necessarily expecting you to know programming in any sense. So yeah, if you don't understand what I said about these links, then don't worry about it. Okay, so here is a function for concatenating two lists. Okay, and again, it has two rules. The first rule says that if you concatenate anything to an empty list, then the result is the second list itself, right? Because if you obviously if you take an empty list and put it in front of another list, well, the empty list doesn't have any elements, so there is really nothing to do in terms of concatenation. So that's why when you append an empty list to another list, you just get the second list. Then here is the recursive case, and what it says is that if I append two lists, one way to compute the output is to say that the first element of the output is going to be the first element of the first list. Okay, and then what I need to do is I need to simply concatenate the second list to the rest of the first list. Okay, so that's sort of what this thing says. So although I defined it as a function, there is a built-in operator in standard ML for doing append, and that is this add symbol, right? So the add symbol is the one for appending lists. So when you say 1, 2 appended with 3, 4, then you get what you expect, right? So the two lists are concatenated and you get 1, 2, 3, 4. Okay, so so here is a way to reverse a list, which again you can understand it as follows. Basically, what you say is that if the list is empty, then an empty list is the same forward or backward. So when I reverse an empty list, I just get the empty list. But if I reverse anything other than an empty list, then what I need to make sure is that the first element of the list should become the last element of the reverse list. Okay. And in addition, what I'm going to do is I'm going to take the rest of the list and I'm going to reverse every element. So for instance, if you have, 1, 2, 3, what this says is that, reverse of this is reverse of 2, 3, right? And then right? So it says take the first element, concatenate it to the end, and then reverse everything else, right? And now if you apply the same process again, then this is going to become, so let's just expand that. That's going to become reverse of 3 concatenated with 2, then concatenated with 1, right? So when all is said and done, you're going to get 3, 2, 1, which is sort of what you expect. Okay. So so once again, it's going to take some amount of practice to go through some of these examples, trying to write out some of these examples before you get comfortable with, how to use lists, okay, and also how to think recursively, okay. So we are going to, now that we have lists that we can use, then we can do something, more interesting. So we will work on this problem called sieve of Eratosthenes, which is used to identify prime numbers. So anybody heard of this Greek scientist? Well, he's the one that is credited with making the first measurements of the circumference of the Earth. Okay, and so he came up with an estimate that is shockingly close. So he is he's a scientist or philosopher from before from BC, right? So before Christ was born. So working at that time to come up with a good estimate of Earth's circumference is something that's quite interesting, or I should say, it's a little unclear because people didn't necessarily know, or people did not know that the Earth was a sphere at that time, right? So that's credited much later during Galileo's times, right? That's 1500 years after. But whatever measurement he made, that corresponds to within 1% of the circumference of the Earth now. So so it's quite quite impressive. But anyway, as computer scientists, we don't, we worry, think more about uh, this procedure for computing prime numbers, which is actually far too elementary as compared to measuring the size of the Earth, right? But so that's sort of the reason why we discuss it here. So the way we are going to compute prime numbers is by essentially crossing out multiples of other numbers, right? So we start with a list of natural numbers greater than one. So that's what we do here. And then we take the first number that has not been crossed out, and we print it, because if it has not been crossed out yet, that means it is a prime number. And then after outputting it, then we are going to cross out all its multiples. Okay, and then we keep repeating this until the list is exhausted. Okay, uh, so at the beginning, nothing is crossed out. So what we are going to do is we are going to output the first element. So instead of outputting, I'm just going to put a circle around it. Okay, so that is, circle indicates it's a prime, and then we are going to cross out its multiples. Okay. Why don't I just do that, right? Because these are all lined up and they're all even. So let's just eliminate them all. Right? So, so we are done. And then now we come back to the beginning of the list and then take the first element that's not crossed out. So that is 3. So we are going to output it. Again, we're just going to put a circle around it, and then we'll eliminate multiples of 3, which means that we're going to eliminate 15, 21, 27, 33, 39, 45, 51, 7, 63, 69, and 75. Okay. And we'll do this again. And now the next element that's left is 5. So we circle that and then eliminate multiples. And where do we have? So 25. And then we're going to have 50 and 75. Let's see, did we miss anything else? 35 and 45, 50, 55, and 65. Okay, so we eliminated all the multiples of 5. And then we output the next, which is 7. And then we have to get rid of the multiples of 7. So 14 is done, 21 is done, and so on. And 28, 35, 42, 49, right? And then 56, 63, 70, and 77. Okay, so those are. And again, now the next thing that we are left is 11, right? And you are going to find that there is nothing left, right? Yeah, so for 11, there are no multiples to get rid of because we already got rid of everything, right? So then we can do 13 and so on, right? So we'll have all the at this point. Well, I guess we forgot to. wasn't careful enough to cross that out. At this point, we should be all left with prime numbers because by the time we get to multiples of 11, we should have exhausted all composite numbers that are less than 100. Okay, so so this is the procedure for computing. This is one procedure for computing prime numbers, and it's one of the first pro one of the programs that people often write when they are learning programming. So let's see how to implement this in standard ML. Okay, so when we implement functions, right? So there is always this difference between scientists and engineers, right? So scientists, by and large, study the natural world and they try to explain, what is in nature, and engineers try to, uh, uh, you know, uh, design new things that will do, what they want, right? So computer scientists are mathematicians on one hand and engineers on the other, right? So on the one hand, we want to study math and understand how functions work. On the other hand, putting on the engineer's hat, we want to design functions that will do the computation that we want, right? Uh, so we have to sort of change our hats, and when we are talking about a problem like sieve of Eratosthenes, we are trying to design a function which has a certain behavior, right? So we need to uh, you know think in terms of, okay, how do I get this uh, behavior? How do I break up the task into smaller tasks? Or how do I take this big function and break it up into smaller functions, each of which I understand better, and I have I'll have an easier time, writing out. So to do sieve of Eratosthenes, you may not realize, but the first thing is, of course, to generate this list in the first place, right? So we'll have to define a function for generating that list, okay? And then one of the things that we did is we took a number and we crossed out its multiples, right? So that is the second task. So we should define a helper function that will take a list and then cross out, which means delete multiples of a given number from a list. Okay, so that is the second function we need. And then once we have these two, then we can design the top level function, because if you looking at how we did this by hand, those were the steps that were needed. First, we needed to generate a list, and then we need a procedure for crossing out multiples. And then once we have those two primitives in place, then we have this simple outer loop which says print the first element and then eliminate multiples of that element. So once we have these two helper functions, then we can write out the top level sieve function, which will eliminate all the composite numbers and then finally produce just the prime numbers. So here is the standard ML code for doing that. So let's look at them one by one, right? So the generate function is the one that's going to generate, create lists of integers, right? So we have, we are going to use two arguments to this, and the way to so in standard ML, right? So in programming languages, you can write documentation in the form of what are called comments. Comments are things that you put in there. The it's something that for people to read. The computer completely just ignores it. So you in standard ML, you put these comments. The comment starts with a parenthesis and a star, and it ends with a star and a closing parenthesis, right? So this is the beginning of the comment, that is the end of the comment, and everything in between, ML is going to ignore. So we just put comments for ourselves, and it says that the first argument is the number of elements to generate, and M is the next element to generate. So if you call, gen of, 5 comma 3, then the result should be a list that has 5 elements starting with 3, right? So it should be this. We expect it to produce 3, 4, 5, 6, 7. Okay. And the way it's going to do that is when you call gen of 5 comma 3, it's going to go match this, and then this is, since this is 5 not equal to 0, it's going to be match this. So this gen of, 1 second. So gen of 5 comma 3 is going to match this rule. And so what it is going to do is it's going to output this number, the second argument to gen is going to be output. So you're going to have 3, and then and notice that this is n minus 1, right? So n was 5, so n minus 1 is going to be 4. M was 3, so m plus 1 is going to be 4, right? So again, n was 5, n minus 1 is 4. M was 3, so m plus 1 is also going to be 4. And once again, you're going to match this rule and not this one. So we are going to end up with, let me just delete erase this so I have enough space. So this is going to become, so the 3 will continue to be there, and this gen is going to become 4 followed by gen of mistake. Right, so there are 3 more elements left, and 5 is the next number to generate. So this will become I keep making the same mistake. Okay, let's see. And so on. One comma 7, and that's going to produce and gen of 0 comma 8 is going to become an empty list. So essentially this is going to become, and now we have a 5 element list starting with 3, just as we wanted. Okay, so that's how this function works to generate a list of elements. Now here is the function that's going to eliminate multiples of a number. And so if you want to eliminate multiples of n from an empty list, then there is nothing to do, right? So the resulting list is going to be just the empty list. If you have a non-empty list, then what you're going to see is you're going to see whether the first element is a multiple of n, right? If it is a multiple of n, that's the check here, right? X mod n equal to 0 means uh, x is a multiple of n, right? So that's the, remember the mod function, which basically computes the remainder when x is divided by n, right? So if x divided by n produces a remainder of 0, that means x is a multiple of n. So what we are seeing here is that is the first element a multiple of n? If it's a multiple of n, then we should eliminate it, right? So we're just going to say, okay, I don't need that element anymore. I am simply going to process the rest of the list to eliminate multiples of n from the rest of the list. Okay, so that's what I'm going to do. If x is not a multiple, then x should not be eliminated. So I'll keep x, and then I'll just go ahead and eliminate multiples of n from uh, the rest of the list. Okay, so that's how eliminate works. And now that we have these two things together, then we can write the sieve function. Okay, so what I have done here is that instead of just outputting the prime numbers, I'm collecting the prime numbers uh, in uh, in here. Okay, so what's going to happen is that if I have to, compute prime numbers from an empty list, well, of course, there is nothing uh, left to do. Okay, so I'm finished, because when I have an empty list, that means I have eliminated everything and there is no more work that is left. Okay, but I'm not going to output the empty list, because the way I have written this function is that I'm going to carry around the prime numbers that I have computed so far in the second argument. So when I reach the end, right? So I have reached the end here. I'm simply going to output whatever prime numbers I've computed so far. Okay. And if I have still elements left in the list, then what I'm going to do is I'm going to say, hey, let me take, see, look at what we are doing here, right? So what sieve does is it takes the first element and it moves the first element to the list of prime numbers, because that's what we did here. We said, okay, the first element that's not crossed out is going to be a prime number. So sieve is going to again take the first element and say, hey, this is a prime number. So it moves it into this list of prime numbers that it is accumulating. And then immediately it's going to eliminate multiples of this number from the list. Okay, so that's really what we are going to do here. We are going to, uh, uh, you know, insert this number, the first number, into the list of primes. And then what we are going to do is we are going to eliminate multiples of this number n from the rest of the list. Okay, so what that will do is this will produce a list where you take this list n's, right, or ns, and you cross out multiples of n from that list, and that is what you will get. And then remember, what we did here is that each time you finish crossing out, we take the remaining list and we apply the same process again all over, right? So that's why what we are going to do is, once we are done eliminating, we are going to apply the same sieve function, right? So each time you execute this rule, what happens is that you go through the entire list once and throwing out some multiples. And once you are done with that, then you're going to come back to the beginning of the list and throw out the multiples of the next number and so on. And that's second phase is done by this second level of sieve. Okay, and once that is done, then this is sort of a top level call what it does is the only reason why I have a separate function here is because I need to first generate the list of integers to apply the sieve to, and then I just call sieve with that list that I generate, and then it basically it's going to produce the prime numbers. Okay, so let's see how we are doing in time. Okay, so what we will do is, would you like to take an early break and come back at 4:15 instead of taking a break at 4:30? So that way, we can just
What's the benefit of doing it now as opposed to at
okay.
30?
There is no benefit. Then we will. The benefit was, I thought there was a benefit, but it doesn't really matter. So let's switch to showing some ML here, so we can work through this sieve code. Okay, so let's. I'm going to. You can see the screen, right? Yes? Okay, good. So let me cut and paste this code. Okay, this is not the one. So that is the gen function, right? So we can call gen, right? So what is this going to do? Gen 03.
Will it just return an empty list?
Right? So because we say, again, look at the comment here, right? Says the first argument is the number of elements. So if I say 0 elements, then the rest of it doesn't matter. It's always going to return an empty list. So now I'm, generating a list of 10 elements starting at 1, and that's what's going to print. Now let me try to generate a list of 100 elements, and ML does not print beyond a certain size. Okay, because there are going to be times when your list has 1 million elements, and then if it prints 1 million elements, then you'll go on and on. So it automatically stops printing after a certain depth, and you can. I think there is some way to change that, but this is typically this just works for us. And if you want to print beyond that, then you can write specific print functions to actually print what you need. So that's the gen function. Now let's cut and paste the eliminate function, right? So remember that it takes a list and eliminates multiples of some number from it. So let us call eliminate, and notice that we already have this generated this list, right? And it calls this, it uses this name IT to refer to this list, right? Which has 100 elements, right? So we can definitely use that list and then try to eliminate, you say multiples of 2 from it, right? So if you do this, then you're going to get numbers up to 100, odd numbers up to 100, right? Because we're going to eliminate multiples of 2. So if you do this, then you see that you have odd numbers. And once again, there are still too many numbers, so it's truncating the list at some point. Okay, and we can do this again. So now, of course, if you eliminate multiples of 2 again, well, it has no effect, right? Because there are no multiples of 2. Now, if you eliminate multiples of 5, then you're going to see that, okay, 5, 10, 15, these numbers disappeared because we eliminated multiples of 5. We can do now 3 and, so on. Eliminate multiples of 13. Well, once again, you don't get. So still there are, more elements left than what ML can print. So so that's sort of how eliminate works. It operates by, removing multiples of a given number from the list. Now we can call the top level function. So let's define okay. So now, so doSieve takes only one argument, right? So which is, how far you want to go in terms of looking for prime numbers, right? So if you say doSieve of 10, it's going to print all prime numbers. It's going to return all prime numbers less than 10. And it happens to list them in, decreasing order. And that's, so it doesn't matter to us because we just want a list, right? So, so we get all prime numbers 2, 3, 5, and 7, right? So now if you say, 100, then, there are too many prime numbers below 100, so we will not see all of them. So let us say 50 and see whether we see all the prime numbers below 50. Well, not really, but it's not printing prime numbers below 7, and we kind of know what they are, right? So 5, 3, 2. But you can also ask, remember we have the remember there is a built-in function called list.length. Okay, so we can use it even when it does not print the whole list. We can use it to print how many elements are there, and it says there are 15 elements in that list. Okay, unfortunately now it has redefined this variable IT to be the number 15, so we no longer have any list to work with. So we need to generate lists from scratch. But you can also do, let's see how long it takes to do to see about 500. Again, it doesn't take any significant time. So one thing we can do is we can do list length of. So what we are doing is we are generating all prime numbers below 100, and then we are computing the length of the resulting list, which is going to tell us how many prime numbers are there below 100, right? So if we do this, I guess I forgot the semicolon, so it's telling me it needs a semicolon. It says there are 25 prime numbers below 100. So let's see what happens if we go to 200. Okay, so that says there are 46. Now let's double that. So 78. Let's double that. So 140. So there is a famous theorem that talks about the density of prime numbers, right? It says, how often do you expect to see a prime number? And basically what the theorem says is that if n is a prime number, then roughly log n numbers later, you will find another prime number. Okay, so it's a very interesting theorem because, well, it's very hard to wrap your head around how does somebody come up with a theorem that talks about how often prime numbers should occur among natural numbers. But it is a very interesting. It is an important theorem because a lot of work that goes on encryption algorithms is based on prime numbers and factorization, and the way you generate some of these keys, right? Keys that you use for encryption is based on prime numbers, and in particular, it relies on the fact that very large prime numbers are not that hard to find because there are, again, prime numbers that occur fairly often. So if you generate a random number and check that it is prime, well, you just have to generate log n numbers around n before you will hit upon a prime number, right? So this is important because these keys that you use in cryptography are very large numbers. These are often numbers that have, 300 digits or 500 digits in them, right? And 300 and 500 digit number, if you think about how large they are, the number of elementary particles in the universe is, can be expressed using a number that has less than 100 digits, right? So when you talk about a number with 300 digits or 500 digits, those are very large numbers, and we cannot, if you use a computer today and you use a computer to count up numbers, then the farthest it can go is about 15 digits, right? Beyond that, it just essentially takes forever to count. So if you want to count anything beyond 15 digits, you're not going to be able to do it. So if you want to generate a very large prime number that's 300 digits, pretty much the only way you can do it is you generate a large random number and magically somehow figure out whether it is prime number or not. There are ways to do that, but most importantly, if prime numbers are very rare, then this process of just generating something at random and checking it if it is prime is simply not going to work. But fortunately, prime numbers are fairly frequent, and so if you have a 300-digit number, you want to generate a random 300-digit number, there is 1 in 300 chance that it will be a prime number. So you just have to generate a few hundred choices, numbers, and one of them will turn out to be a prime number that you need. So anyway, that's sort of a side discussion. So this procedure is fairly efficient. So we can definitely try how far it'll go, right? So let's try 10,000, and again, it doesn't take any time. So let's go to 100,000. Well, it is taking time, right? So at 100,000, it's beginning to take some amount of time. And if we I don't think for 200,000 takes time. We can still wait, but around 400,000, we'll probably find that it's going to take a very long time, much longer than we want to. Well, it is going to be within what we can wait, but it's pushing it. Right, so there are 34,000 prime numbers below 400,000, right? So it can go quite far. You will find that standard ML is not a particularly fast implementation. So there are languages in which this can be done in much faster, probably easily 100 times faster, right? So that I can tell you for sure, possibly 1,000 times faster, right? It depends on a number of factors. Standard ML is not designed for efficiency. It's designed for making it possible to write programs very concisely and in a way that looks very much like math, and doesn't have to do you don't have to spell out things in too much detail. Okay, so if you write this Sieve of Eratosthenes in a different language, you will find that the programs tend to be somewhat larger, right? So if you try to write it in Java, the program will probably be at least twice as large. Okay, and there are going to be programs where the ML program will be like 1/5 or 1/5 of your Java program. So it's definitely much more concise and clean, but it is not necessarily the fastest implementation. So Java implementation probably won't be that much faster, right? It'll be faster by at least a factor of 10, maybe 50, but not, definitely not hundreds. Okay, so let's break here, and we'll come back and pick up from where we leave off. Also, as we go into recitation, we'll meet right here in the classroom. But if you have any questions relating to the material we have covered in the class, in the last several lectures, and relating to your exam, then feel free to bring those up. I will answer those, and then we'll continue to study more ML. Okay, very good. So let's take a break for 20 minutes. We'll start at 4:40. Okay, see you then. Okay, so let's get back to the class. Maybe one more minute. Okay, so I'll wait for one more minute. Okay, so what we'll do from here on is we are going to go back to some of the definitions that we have, some of the concepts we have defined from the beginning of the course, and try to take those definitions and express them in ML, right? So hopefully that'll serve as partly as a way to learn ML, and at the same time, it'll also help you sort of prepare a little bit for uh, to sort of review the material that we have covered in the course so far. Okay, so let us start with sets, which is one of the first things that we discussed. So we just learned about lists in standard ML. Sets are obviously similar, right? Because they are also collections, just like lists, but they're not exactly sets because lists are sequences where the order matters, and you can have duplicates, right? So it's perfectly fine to have a list where you have 1, 2, and 1, 3, 1. This is a perfectly valid list. Obviously, it's not a set. So sets and lists are somewhat different, but you can say that lists are more general, because unlike sets, right, every set can be represented as a sequence, but some sequences don't correspond to sets, right? So just like this one with repetition. So so what that means is that we can represent sets using lists if we are careful to avoid duplicates and such, right? And also the order doesn't matter, so we need to be careful about that. So one way to do that is to keep So if you keep the elements in a sorted order, then there is exactly one order in which the elements are going to appear. So the order no longer, differs, and so you will have, you eliminate order as a factor. And secondly, if you eliminate all the duplicates in a list and keep all the elements of the list in a sorted order, then lists can pretty much model sets. Okay, so that's what we are going to do for our discussion of sets. We are just going to use lists in standard ML, except that we are going to keep these lists in a sorted order at all times. Okay, so that way we won't run into some of the problems with lists, such as having duplicates. So let us take some of the set operations and see how those operations can be expressed in standard ML, right? So the Cartesian product is defined this way, right? So you take any element from X and any element from Y and make a pair out of it. So you express that formally by saying that X cross Y is the set consisting of pairs of the form x comma y, such that x belongs to the set capital X and y belongs to the set capital Y, right? So now we can express that, fairly in a fairly straightforward way in standard ML. But it's not going to be exactly the same thing. And there is a reason, because the reason is that this is basically a logical formula, right? So it's not exactly a function in the way that we define functions. And if it was a function, then there would be a almost exact translation, or the translation into ML will not look that different if this was a function, but instead we are defining it using a logical formula. And that means the ML definition is going to be somewhat more involved. And the way we are going to do that is we are going to split it into two functions. The first function simply takes one element X from the set X, and then it forms pairs with every element in Y, right? So that we call this as a cart1 for lack of imagination, right? So I call it cart1. It basically takes one element from the first set and forms pairs with every element of the second list, right? So it takes X, and then it takes the first element of the second list, and then forms a pair X comma Y, and then it calls itself recursively on the rest of the list, which means that if you start with, if you call cart1 of 5, then what it is going to do is that's going to call, this is going to match this rule. So you're going to have 5, comma, the first element of the list, which is 1, right? And then it's going to be cart1 of 5, and then the rest of the list, right? And then this cart1 is once again going to match this rule. So you're going to get 5, comma, the first element of this list. And then there's going to be recursive call to 5. And, so you'll end up eventually, after one more call, you'll end up with right. So you have formed pairs with every element in the second list, right? So you get 5 comma 1, 5 comma 2, 5 comma 3. Okay. Now this function, the higher level function, which I call as cart to stand for Cartesian product, is going to iterate through the first list. Okay. And so what it does is it's going to compute pairs, right? It's going to call cart1 to compute pairs where the first component is going to be the first element of this, and then it's going to call itself on the tail. So if you look at exactly how this works, let's try to take right. Let's see what happens here. So this is going to match, obviously the first argument is not nil, so it's going to match this rule. And so we are going to end up with cart1 of first element of this list, which is 5, and ys, which is the second element, right? So 1, 2, 3 appended with cart of excess, which is the tail of the whole list. So the tail of this list with 5 and 6 is 6. And this is still y, so it should be 1, 2, 3. And cart 1 of 5, 1, 2, 3 is what we have already, computed here, right? So it's going to be this 5, 1, 5, 2, 5, 3, appended with card of 6, 1, 2, 3, which you can believe me when I say, at this point, this will give you and then you will end up with the base case. So that will be empty. So the net result will be right. So that is, of course, the Cartesian product of, if you think of these two as sets, then this is the set consisting of the Cartesian product of those two sets. Okay. Any questions? Okay, so let's take another operation like union, right? So union is, again, defined this way. So the union consists of elements A such that A belongs to either X or Y, right? So that's what this definition says. And we, again, translate that into standard ML like this. And once again, there is a little bit of gap between this definition and what we have here. Once again, because this is a logic definition and this has, what you can express in ML as a function. So, but we can, it's not that difficult to make the leap. So we have to define the base cases, right? So it's clear that the base cases correspond to one of the sets being empty. So if you have an empty set union with another set, the result is going to be the other set, right? And so we have, we handle the case that the first list is empty, the first set is empty, then the result is the second set. If the second set is empty, then the result is the first set. Otherwise, we have the inductive or recursive case where neither set is empty. Okay. So now if neither set is empty, then we can check if the elements are the same. If they are the same, then we are going to output it just once. If they are different, then we may end up outputting both. So so that's what we do, right? So if they are the same, then we output X and then we union the rest of the sets, right? Because we know that Y is the same as X. So Y does not have to be included in the union the moment we decided to include X. So that's why if X is equal to Y, then we output X and then we just go on to the rest of the two sets. But if they are not equal, right, then we have this condition here, which if you think about, purely in terms of sets, it doesn't have any role to play. but the reason why we have it this way is because we are representing sets using lists. And when we represent sets using lists, we want to make sure we can assume that they are the numbers, the elements are going to be appearing in increasing order. And what we want to do is we want to make sure that we maintain the list in increasing order. So if x is less than y, then we first output x, and then we say, hey, I'm just going to call the union on what is left. But if y is the smaller number, then we will output y first and then call union of the the remaining elements. Okay, so that's how we define in the union function in ML. So what I would like you to do is to try out some of these other operations yourself. So intersection, for instance, is going to be very similar to union, right? For instance, if x is equal to y, then in the intersection, that element is going to appear, because for an element to be in the intersection, it has to be in both sets. So in this case, in the case of intersection, you will have x in the output, but in these two cases, right, you have a situation where the element x or y doesn't necessarily appear in the other one, so you're just going to drop it. So it'll become, for instance, in this case, so if you're defining intersection, it's going to look very similar. It's going to look here, in this case, as a recursive call to intersection of. So because x is in both lists, so of course it's going to be in the output, and then you're going to call the intersection of on the remaining elements. So in here, you're going to have x is less than y, so you know that x definitely is not in the second set, right? Because remember, y is the smallest element, because everything is sorted. So y is the smallest element in the set. And if x is less than the smallest element in the set, then you know that x is not in the set. So therefore, when you do the intersection, the x is going to be dropped. So it's just going to be intersection of xs. And in the same way, in the third case, is going to be intersection of so intersection is going to look, very similar to union. Subset is almost trivial because it just says, x is a subset of y if x union y is y. We already defined the union operation. So all you need to do is to check whether if you compute the union, you get the second set. If you do, then you know that it's a subset. So, and then, you should try to define the difference, which is going to be a little bit more, it's going to require, it's not as easy as, these examples. Of course, you should also define, membership. Okay, so I will hand out the next homework towards the end of this week. Okay, I probably won't have all of the problems for the next homework, which will also be obviously your last homework, right? So I'll give out some problems so that if some of you, prefer to do some work and get ahead next week, then you can do it. If not, you can, get it done in the last week or after the last day of classes. So we have almost one full week between the last day of classes and no, it's more than that. It's like 11 days, right? So we have 11 days between the last day of classes and your final. So so you have some time to prepare. Okay, so you should, some of these problems will be included in your homework. So you can, get to practice some ML and be So that way, if you start doing some of this, then the next time you come to the class, you will have, it'll be that much easier to get through the rest of the material. So now that we have defined sets and operations on sets, we can then talk about relations, because relations are a subset of cross product of sets. So we already have seen how to represent sets in ML, how to do cross products, how to do subsets, and so on. So we are basically ready to talk about relations and examine properties of relations, such as what is the domain, what is the range, what is the is it one-to-one, is it on-to, is it bijective, right? So all of these we can answer because we have covered whatever we need in terms of background. Okay, so remember that a set is a subset. A relation is simply a subset of the Cartesian product. So it's in ML, we are going to represent a relation as a list where each element is a pair, right? So that's really what we're going to do. And we're going to cheat a little bit by, by pretending all sets are subsets of natural numbers. Okay, so that will keep our, make our life easier because representing other types of elements is, it's going to make things a little bit complicated, because ML will insist that it be able to figure out the type of the function, and then if you, it will very quickly assume that things are lists of integers, and then if you try to give it lists of something else, it'll start, complaining about type error. So to avoid some of that ugliness, we will simply stick to, by and large, sets of integers. So that way we are less likely to run into these types of errors. So here is a function for computing the domain. Remember, so the domain, for computing the domain, what we are going to do is we are simply going to take the first element of these pairs, right? So remember our arrow diagrams, right? So we have X, Y, and here is 1, 2, 3, and 3, 4, 5, and we have arrow from 1 to 3, 2 to 4, 1 to 4, and 3 to 5, right? So this is what we have. This is a relation that we have, right? So to get the domain of this particular relation, what we are going to do is we are simply going to traverse through this set and pick up all the first elements, right? So those are the tails of your arrows, right? So those tails we will pick up. And similarly, if you want to get the range, then we are going to simply pick up the second elements here, right? And so what we do is that, okay, so obviously if there is a relation itself is empty, then the domain is going to be empty. If the relation has some elements, then what we are going to do is we're going to pick up the first element of the first pair, right? And then we are going to then call get domain on the rest of the list so that we pick up all the first components from there. And then we are going to call union because we are going to apply set union. Because if you don't apply set union, then notice that we have the first component here occurs twice, right? So it's 1, 1. And so if you don't call union, if you just accumulate the elements, then what we get here as get domain will have duplicates. So to avoid duplicates, we simply say, hey, why instead of appending lists, we are simply going to use the union operation so that it will automatically eliminate the duplicates. Okay, so that's why we have defined it this way. So get range is very similar. We are going to, instead of picking up the first component, we are picking up the second component, but otherwise you can see that the functions are essentially identical, but for the difference that you're picking up the first component here and the second component here, right? So this is going to get you the range are all the elements that have an arrow coming into them in Y, right? So it's going to pick up, get range simply picks up all the elements that have an arrow coming into it. Get domain picks up all the elements in X that have an arrow going out, right? So then we can define, other functions, other criteria, like, is this a total function, right? Remember, a total function means that there should be an arrow going out of every element in X, right? So that's why, so remember, get domain tells you the set of elements that have an arrow going out, right? If that is the same as the entire set, then that means that there is an arrow going out of every element in the first set, and therefore it is a total function. So we can very easily define a total function based on get domain. And similarly, is onto means there is an arrow coming into every element of this set. So get range gives us all the elements that have an arrow coming into it. If that set is equal to the entire set B, the second set, then we can say that it is an onto, right? So notice that to define whether something is total or onto, we need these sets, right? So to see if a function is total, you need to be given what is this set. Similarly, to know whether something is onto, you need to be given the second set, right? So those are the additional arguments that these functions is total and is onto they take. Any questions? Okay. So now let's So now what we are going to do is we are going to define two other functions, one called getTails. And you can see that getTails is, compare getTails with getDomain, right? Stare at it for a little bit. You will see that it's almost the same. And the only difference is that this one uses union. This one simply adds X to the list. Okay. So which means that if X occurs in multiple pairs, then it's going to be represented multiple times over here. Okay. So for instance, in getTails, so getTails is going to, if you take this example, getTails will return, right? It's going to say, hey, this is, it's going to look at this pair and say, hey, I'm going to put one here. It's going to look at the second pair. It's going to put it, it's going to look at the third pair, and it's going to add one again, and then fourth pair, and then it's going to add 3. Right? So essentially what it is going to do is it's going to count, put the element here anytime there is an arrow coming out of it, right? If there are multiple arrows coming out of an element here, then that element is going to appear multiple times. So if there are 2 arrows coming out of an element, that element is going to appear 2 times. If there are 3 arrows coming out of an element, it's going to appear 3 times. Okay. And same way about heads, right? If there are multiple arrows going into an element, like 4 here, right? So there are 2 arrows going into 4. So this one is going to have, on the example, it's going to result in 3, 4, 4, 5, right? So the main point is that if there is exactly one arrow coming into each element in Y, then there won't be any duplicates here because there is only one arrow coming into it, right? So if there is exactly one arrow, then there will be no duplicates, and in addition, none of the elements here will be missing, right? Because and so if we have exactly so that allows us to define things like is one-to-one, it's a function, and so on. Okay, so let's go through this and try to understand, right? So get domain basically says what are all the elements that have at least one arrow going out. Okay, now get tails is similar, except that if there are multiple arrows going out, it's going to contain it multiple times. So for instance, in this example, right, so get tails is going to return 1, 2, 1, 3, whereas get domain is going to return 1, 2, 3, right? So if you check, are these two equal, then ML will say, no, 1, 2, 3 is not equal to 1, 2, 1, 3, right? And therefore, it'll say it's not a function. Okay, so why is it not a function? Simply because there are 2 arrows coming out of the same point, right? So the definition of a function is there can be, at most 1 arrow coming out of a point. Okay, so get domain, gets all the elements that have, 1 or more arrows coming out, and get tails also gets it, except that it's going to represent any element that with multiple arrows will appear multiple times. So therefore, these two will be equal only in the case where there is at most 1 arrow coming out of every element, right? So this is capturing the at most one arrow out property, right? Because if it's at most 1 arrow, then nothing will be duplicated here, right? And this will contain exactly the set of elements on which there is some arrow coming out. This one always captures, exactly the set of elements that have, 1 or more arrows coming out. If the 2 are equal, then okay, there is at most 1 arrow coming out. So what this one is checking is, at most one arrow in, and the logic is the same. Get range is going to count anything, all the elements that have 1 or more arrows coming into it. Get heads is also going to, contain elements that have 1 or more arrows coming into it, except that if any element has multiple arrows coming in, that will be represented multiple times. Okay, so the set of elements will be the same, but if there is more than 1 arrow coming into any element, that element will occur multiple times on this set, and therefore the 2 will not be equal, right? So if they are equal, that means any element into which an arrow is coming in, there is at most 1 arrow coming into it. Okay, so that's why you can define, one-to-one in this way. Okay, remember our terminology. The other term that we use for one-to-one is, injective, right? And onto, we call it surjective, right? So, so these are ways to get our definitions of functions, total functions, injections, surjections, and so on. And bijection is, of course, simple. If you go to your book, it'll say a bijection is a total function which is both one-to-one and is onto. Okay, so we just combine all of the conditions together, and then that tells us, okay, it's a bijection. Okay, so once you've defined all of these, then figuring out whether something is a bijection is straightforward, which is also the case when you work out the problems by hand. You have to check whether it is is a surjection or injection, and then once you have done that, answering whether something is a bijection is straightforward. So what I would like you to do is I'd like you to try some of the other concepts that we have looked at in relations, such as composition of two relations, or powers of a relation, where a power is basically R square is R composed with itself, R cube is R composed with R itself 3 times. And you will remember that if we represent R as a graph, then R power n will consist of all pairs such that there is a path of length n in the graph of R, right? So Rn, so x comma y is an R power n if there exists a path of length n in the graph of R, right? So that way there is this close relationship between a graph representation of the relation and the powers of that relation. Okay, so so checking for reachability in a graph is very similar to computing R to the power n, right? So here are some of the other problems for you to try out, right? Obviously, you won't have time to try each one of them, but try whatever you feel is interesting or approachable, right? So, so again, obviously, you have to start with some of the simpler exercises, but as you get more comfortable, then you can address some of these. Okay, so so that's about relations. So we looked at sets and we looked at relations. Now let's look at counting, right? So that's something else that we did, mathematically. And now let's see how, if we can turn that mathematical thinking into a program. Okay, so for counting, we are going to start by generating combinations. Okay, so so how do we generate combinations? We so when we generated combinations or subsets, right? So as we call it, right? So given a set of size n, or rather given a set of size m, then we want to generate subsets of size n. And we didn't really give a recursive formulation of how we would go about doing this job. Okay, so let's first see if there is a recursive way to solve the problem, right? So so at the top level, there are two choices. The subset either contains the first element or it doesn't contain the first element, right? So if the subset contains the first element, then what you can do is that you can pick the first element and then say, hey, give me a subset of the rest of the set that has n-1 elements, because I already have picked one element. So I'm just going to go and pick a subset of size n-1 among the remaining elements. But if I went with the choice of not including the first element, then I have to pick an n-member subset of the remaining elements, because obviously I'm trying to pick a total of n elements. Okay, so let's do that. Okay, so this is the recursive formulation we are going to work with. We either pick the first element or not, and then once we make that choice, then we do this recursively from then on. Okay, so yeah, I guess so this is similar to the function that we already defined before, which we call as gen. Maybe a little different, or maybe it's exactly the same, but looks like I forgot that I already have a function. So you can sort of ignore this more or less. Okay, so that because we have already done this. So now let's forget this. So let's focus on this function, which expresses the logic over here, right? So what it says is that if you want to pick a subset of size 0, right, then there is always one subset of size 0, which is the empty set, right? So subsets of, so what we are, the way this function is set up is that this is a set, right? And the second argument specifies, what is the size of the subset that you want. Okay, so the base case says that if you want a subset of size 0, then you always have 1, no matter what you start with, right? So the set itself doesn't matter. It always has a subset of size 0. Okay, now when we are representing subsets, so that means we have a list of lists, right? Because each set is going to be a list in itself. So if you want a set of sets, right? So that means, we write with, right, multiple braces like this, right? Right. So if you want to write out the subsets of the set 1, 2, then it'll be a set of sets, right? The same. So therefore, when we ask for subsets, we should expect that we will get a list of lists where each element of the outer list is a set. Okay. So the base case basically says that there is always this empty set. So now the second base case, what it says is that if you have an empty set, okay, and if you want to make a subset of size n, right, and notice that n is, greater than 0, because if it is 0, then it is this rule that would have been applicable, right? So if you are here, that means n is not equal to 0. So if you want a size, if you want a set of size greater than 0, but your starting set is empty, then obviously there is no subsets of size greater than 0 for an empty set. So we are going to return the empty set here, right? So you may remember a bunch of problems that you were looking at before the first midterm, which often tries to confuse you with empty set versus the set containing an empty set, and so on. And here is an example why that confusion, you need to get through that confusion and really understand, because here is a case where you have a set consisting of the empty set, whereas this is an empty set by itself, right? So this is a set consisting of one element, which is the empty set. This is just that empty set, right? So so the two are different, and if you get this wrong and instead you change this to just the empty set instead of the set consisting of empty set, then you should definitely try that, right? It won't be an error. The ML won't complain to you that there is a type error or anything like that. It is just that you'll get an unexpected result. So you should definitely try that. Just replace this, right? You replace that with just that, and then you'll see, magically there are no subsets to anything. Okay. Okay, so once we have gone through those base cases, then let's look at the recursive case, which is the logic of the recursive case is what we spelt out here. So there are two cases, one in which we pick the first element and the other in which we don't pick the first element. So here is the case where we don't pick the first element. So we simply say, hey, let me not include the first element. So let me just drop X, and let's look at just the rest of the set and pick a subset of size n from the rest of the list. Okay, so I'm going to get a bunch of subsets that way, and I'm going to concatenate that with a bunch of subsets. Yeah, so this is and this set of subsets corresponds to the first case here. So what we are going to do here is we are going to pick the first element, and then we are going to form the subsets of the remaining elements. But we are only looking for subsets of size n-1. And then once we get those subsets, we are going to put X back in each of those subsets. Okay, so prefix all is going to take this one element, and it is going to put it in front of every one of the subsets returned by this call. Okay, so that's exactly what we do. So we take the n-1 member subset of the remaining elements. That is what this is. And then we combine it with the first element, right? So for that, we have written this function called prefix all, which is going to combine this first element with each of those subsets. And then that's how you generate the subsets corresponding to this case. And this corresponds to the subsets for the second case. You put that two together, and you'll get all of the combinations. And then at the top level, I have a function for m choose n, which is going to generate all of those combinations and simply count the number, right? So, so this way you simply generate and count. So obviously generating and counting is a lot more work than doing a simple math calculation as we do in the course. But what you will find that is the advantage of programming is that sometimes the problem is not easy to solve. It doesn't admit a simple analysis and closed form solution like the way we have seen it before. In those cases, you can still write a program, and if the numbers involved are not too large, the program will generate those combinations and will give you an answer. Okay, so so let me not talk about permutations, but instead to make this point, let's go to one of the counting problems that we have looked at in class. Right, so remember this problem where you have a bookshelf and you need to pick n of m books, but there are additional constraints that once you pick a book, then you have to you cannot pick the next k books, right? So this was a problem that we worked out, and the solution involves mapping this to a sequence of zeros and ones, right? So the ones kind of represent the books that you pick, and it's a little bit more complicated because each one also says you're going to not pick the next k books, right? So I'm not sure whether you remember, maybe you are preparing well for the exam and you already done the preparation, so therefore you remember this problem well, or maybe not. Okay, whichever it is, we can do this kind of counting using a program. And what you will notice is that the program for picking these books is very similar to the one to the choosing thing that we picked up. Notice how the first case is a set consisting of empty set, the next one is the empty set, and then the third one has these two cases, and it's exactly that kind of logic here. We are if there are no books left to pick, then you will return this. If you've exhausted all the books and you still need more books, then you'll say, well, I know I don't have any way to choose those books. And for the recursive case, you are going to have either choose the n books out of the remaining books, leaving out the first one, or you are going to pick the first one, right? And so you're going to use the prefix all to combine the first book with other books. The only difference between this function here and this one, which if you could see, you'll be able to appreciate, is this call, right? Instead of this drop n, there is going to be just excess, right? So what this is doing is that once you pick the first book, you have to drop the next k, right? So that's why you first call this drop n to drop k books from the beginning of excess and then make your choice. So other than that dropping, this function is going to look exactly like the subset function that we looked at. And that kind of shows you how additional constraints can be easily added to your program without having to really think about the problem fundamentally in a fundamentally different way, right? Because sometimes we are clever and we can figure out how to model the problem, and other times, well, it doesn't come to us, and then we can apply a little bit of brute force, and that's where our programming ability helps us. Okay, very good. So let us stop here. I think we have done a good deal of ML programming today, we will continue after the exam and after the Thanksgiving break. So do you have any questions, or are you tired out and ready to go home? Okay, so good luck with your exam. If you have any questions about the exam, of course, you can continue to post on Piazza, and we'll try to answer it as soon as possible. And your next homework will be posted later this week, and so you should definitely take a look at it before you start the break, and then you decide whether you want to work on it during the break or you're going to just take a week off, right? Very good. Good luck with your exam.